Yeah. So those of you that wanted to review the lecture from Friday, for some reason it didn't record my voice, I think. Right, Anne? Yeah. So if you have questions, I can have extra office hours to explain, but nobody shows up in office hours except the few that always do. So I think you're all set. You don't have to show up, really. I have other things to do, but I'll be happy to see you. But anyway, if you have questions on previous lectures, you can always request extra office hours that matches your time, or just show up in hours of office hours. Attendance is low, but I guess it's okay. So what was the problem of forward kinematic? Yes.
Like variables to figure out the time vector position.
Right. Correct. Why is this like that? I don't want. Okay. So problem of forward kinematic. You will find an expression, or you find the system model, right? Your robot, using all the two different methods we have. And if you plug in the values for joint variable, which are your input, you will get the position and orientation of your end effector, which is your output, right? So my hand is here, it's like 45 degree, well, this is 90 degree, 45, and then 90, this position is the end effector position. That's the problem of forward kinematic. Now the problem inverse kinematic is, so we have the same robot, we know the forward kinematic model, we already modeled it, right? Let's say the PA2, you modeled your system, basically, right? The kinematic of your system. Now, I would tell you this end effector has to reach this point. You know X, Y, Z, and orientation of this point. So you know all the 6 elements here. How do we change the joints? What are the values of joints in order for this end effector to reach to this point? So you have to find theta 1, theta 2, theta 3, right? You can use the function, the system that you have, the function subfunction that you have. Now the thing is, how many ways I can reach this point with this robot? A lot, right? So the problem of inverse kinematic is more complicated because there exists more than one solution, right? Now you have to think about, is this solution is what I want? So one of your, well, your next programming assignment after holidays would be track, let's say either a circle or writing. So you have a 2-hour robot that has to find points, you know, on a path. So let's say track a trajectory. It could be anything. Now, if I need to go here, if my robot is moving, the next one is here, I'm going here. So since the robot is moving this way, so the solution that is as smooth and close to the previous solution is accepted, right? You don't want to go very quick here and then come back here and come back there. Does that make sense? So then you will choose the solution based on what the application is. You'll have multiple solutions, you have to choose one. When you code, you can always compare with the previous solution and choose the one that's closest to set a threshold. All right, because both of those are correct, and you'll see. I will show you the 2-hour robot for this example, and you see that there's a righty and lefty solution for that. So a little bit of critical thinking, problem solving, engineering part comes in handy when you are dealing with inverse kinematic. Okay, and you have to consider those when you are, if you're writing a code or writing an algorithm, or even if you're using analytical methods, you have to mention there are this many solutions, and then depending on your initial condition or the application of the robot, you choose the proper solution. All right, make sense? There are 3 different approaches to solve inverse kinematic. We will start from the easiest one, which is the geometrical solution. You're using sine, cosine, trigonometry. I always cannot pronounce that. Trig, trig, easier. Use trig basically to find a solution. Then you have analytical method that you will go and find the inverse position and orientation. You basically divide the problem into 2 subsets. Position, orientation, you find them, and then you can always merge. There is a certain condition you can do this. The third method is numerical method. Use Newton-Raphson method. You just solve step by step. You can use incursive method. Guess something and try the basics of Newton, right? Like how close you are, and then find another point, you get to some threshold, you say, I'm good. That's how you solve it. So I think this is good enough. And this is the next thing that you can use. I will introduce the numerical method, but I'm not going to enforce it. It's basically, you can just grab the algorithm online, just open on the, like you can grab the algorithm and then just use it. So we're not going to spend so much on that, right? There's no point. But these two methods, there's a little bit of exploring and discovering, which we will focus on that. Today is geometry, because I think it's fun and it's easier to follow. Well, more straightforward to follow, okay? Now, what I will do is I will solve one problem, and your second problem is your CP15. It is easier than the problem I will solve, but I want you to spend time on it, and then there are actually real values that you have to solve. It's due by class time. All right, so listen or pay attention when I'm solving mine. Adnan, are you listening to what I'm saying? He's sitting right in the front. All right, so think of a two-link planar chain or 2R robot. If you want to find the position of this, let's forget about orientation for now. This is planar in 2D, so we're not really concerned about the orientation of our end effector. You have used this to find the singularity, something like this before, right? So you're very familiar with how forward kinematic looks like. We use graphical method or geometrical method to find X and Y, right? You should be familiar with this. So X and Y, the position of your end effector is the function of θ1 and θ2. Now, if that is our forward kinematic problem, right? If that's our system, our inverse kinematic problem becomes, if you know X and Y, the position, X and Y of the end effector, find what is θ1 and θ2. From this sketch diagram, you can see that there are two solutions for this, lefty and righty, right? So the solution to this kinematic problem is going to be both of those. Depending on which direction your arm is moving, one of them will be accepted, right? Now, how did we find the solution? We use the geometric solution, geometric method to find that. So one thing that is really useful is law of cosine. Are you familiar with law of cosine? You remember it? Let's see. This is R. This is L1, L2, θ2, θ1, and beta. All right. Law of cosine. We're going to use it, I think, on Monday. But if you wanted to know how we got this, because you see this cosine appeared here. Law of cosine tells us that R square is L1 square plus L2 square minus 2L1 L2 cosine of the angle that is in front of this R, whatever edge that is. So cosine of here beta. So you can write this expression for any of those. So in this triangle, if I wanted to find L2, what would I write from law of cosine? Someone? Yes. Correct. So L2 square equal to the other two left, L1 square plus R square minus 2 times L1 R1 and the angle in front of it, cosine of alpha. So if we have three of these values, we can find the fourth one. So you can find the angles basically using cosine, law of cosine. Now, why is this important? So we are trying to find our joint variables, right? θ1 and θ2. We have to find expression for theta 1 and theta 2 are joint variable based on the existing information. So now here, all of these L1, L2, X1, X and Y, these are all known. If they are all known values, you can find beta and alpha. If you find beta and alpha, you can find theta 2, right? Then you can also find theta 1. If you know what gamma is, then you can, and if you have alpha, you know that is gamma minus alpha is theta 1. The problem of inverse kinematic, we need to find solutions for joint variables, right? They're always trying to find joint variables, a function of whatever we know in the system. So we will write expression to solve that. Make sense? Where do I get X and Y from? It's given, right? So X and Y is the position of your end effector that I gave you. Where do I find L1 and L2? Is the structure, right? The robot, L1 and L2 length of the link. So you have all of these values. Now you can find these relationships. Then theta 1 and theta 2 are based on these relationships. So the next example we're going to solve, so this is in 2D. So I'm going to use a 3D example that has a revolute joint and prismatic joint. So you see kind of everything together. And then your example is going to be a bit simpler than that. So if we have a cylindrical robot that looks like this, I've given you all the axes, just make your life easier. We are going to find inverse kinematic expression for this robot. Once we have the expression for any given coordinate of our end effector, we can find our joint variables, right? Now, first of all, what is the joint variable? Adnan, what are our joint variables?
Theta 1, D2, D3.
Theta 1, D2, D3. This means that I have to write expressions to find theta 1, D1, D2, and D3. So to do this, let's see, let me write the question. So if you're coming back to this, you know what the question is. The question is, find inverse kinematic expression given, I'm going to call this P03, right? Given P03, X, Y, Z03. Ignoring orientations. This means that I'm not right now caring about the theta X, theta Y, theta Z. You can find it from different assignments, right? So for now, like you know the initial value, but we are right now, we're not caring about the orientation, just thinking about the position, just to make it simpler. So the first step, we have to identify how many joint variables we have. We've done that. So that's your first step always. So I'm going to say step 1. Then, so we're going to use trig to find this. So if you look at plane, I think I started with X0, Z0. Okay, if you, let's start with X0 and Z0. So in X0, Z0, so this is your X0, Z0 plane. So if you're looking from this side, right? You're looking sideways. Which of the joint variable you will see when the motion happens? If we are at this plane, right? The plane that you're looking at. Let's say the robot starts moving. Which of those joint variables will be visible? D2 and D3. So right. Good. So That is our step 2. We are going to sketch what we see from the plane we chose. So we need to go to as many planes as possible. So we have 3, right? To make sure that we see all of the joint variables there. So you realize that you will definitely see D2 independently. You will see D3, but if this joint moves, you will see a different length of that part, right? So this means that that's not independent. You have to find another plane that will show it independently without changing, without being dependent on some other plane. So again, you're just using graphical knowledge to solve this, right? So let's redraw this in X0, Z0 plane. That would be your step 2. So I'm gonna model that with a box. It's fine. This is another box for my prismatic. Another box for my prismatic. There's this line I see here. Right? That's basically what we see from the side view. I'm gonna say this. So I'm gonna put all the frames now. This is X0, Z0. Now, I know I will see the length of this as A1. No problem there. Then for this box, I will see Z1, X1 frame. So I'm gonna show that. I also see A2, right? And then I will see D2 here. So that completely is independent, and I will see the whole thing. And then here, Z2, Y2. And last frame, here, Z3, Y3. What else do I see? I see, is this A3? I can't read it. I see A3. And also, is that me? Probably. E3, right? These are all the things that I see from this view. So next thing you do is check which coordinate of the end effector you can see in this view. I can see Z03 and then X03. Again, we are finding this coordinate in space frame, right? So we have been given the coordinate in base frame, so we're going to write everything for that. Now, write a relationship for Z03 based on what you have there. So this is the part that I say is fun because it should be like visual. You can visualize it, right? You can just see it from there. So Z03 is A1 plus A2, right? The length of the fixed part of the link. And then what is in there? Plus whatever D2 is, however much the prismatic zone goes up, right? So it would be A1 plus A2 plus D2. Now, what was our objective? Why are we doing this? What are we trying to find? An expression for D2, right? So I'm gonna say D2 is whatever Z3 is minus A1 minus A2. So A1 and A2 are given because part of your system is the structure, the link length does not change. Z03 changes based on whatever the input you get from the user or wherever you want the end effector to end up, right? Mask, please. You look so handsome too, almost too handsome. Without mask. All right, so that's for D2. Now, we could write an expression for X03, but as Michael said, if we have a rotation in the base, the length of that part is going to be affected, the amount that we see from this frame, right? So X03 is dependent on something else. So we're not going to write anything for X03. We don't have anything else, right? So we have to go and move to another plane or another view, if you will. What's the other view that we can use to find the rest of our joint variables? XY is the top view, right? If we go to top view, because the rotation is happening in that plane, so we will see theta, and then we will see what else we can get. So at least we know theta 1 is going to be seen from that plane. Sometimes you have to write all 3 planes. Sometimes you'll be good with 2. Really depend on the configuration of your robot. So let's check plane X0, Y0. All right, so we will see our revolute joint. I'm going to show this circle. And then what I'm going to do is I'm going to actually use a larger, bigger one so I don't run out of space. I'm going to put my base frame in here. Base frame will not rotate if everything else rotates, right? So base frame is fixed. Now, to help us, just to make things simple, I'm gonna assume that my first joint rotated a little bit. So I wanna see what will be the configuration of the rest of the robot, all right? Let me make this one green, and then I'm gonna draw everything else blue. So if this rotates, I'm gonna see my prismatic joint, if it was a box, right, a little bit rotated. So this is the base of X0. Now, from top view, you see both of those two on top of each other, right? So basically, both of prismatics are here. Now, we are done with that. Then what else we see? We see a line, right? This line is A3. It moves E3. Then we have Z0, Z3, and X3 for our end effector. That's what we see, right? Let's put the rest of the frames and then write the relationships. So what I see from these two, X1, Y1, for one of them, so I'm going to show here, X1, Y1, and for the other one, I'm going to just continue. That one's going to be X2, and then not the Z2. Z2 and X2. Okay. We also have to show theta 1, right? This is the color. Theta 1. This is how much that joint rotated. Now I see theta 1, D3, and both of these are independent from other things that happens in other motion that happens in other planes. So I can't find two relationship with this, and I'm done because I already found D3, right? So write these relationships. When you solve this in your homework or exam, you have to be as detailed as I am, right? You have to have all of this. Every one of these will have a point for you. Now let's just start with D3. How can we find D3? Like what relationships do you see here? Let me add one more thing, maybe that will help. Here, this is Y03, and this one is X03, right? This is end effector, and this is the position. So what relationship can you write to find D3? Yes, Justin. Yes. Can we write something that's not dependent on theta 1? Because it's best if you can find like linear relationships, so they are independent from each other. That's not wrong. you will have to find theta 1 and replace it. So can we find something else? Adnan?
Could you do root quantity of y03 squared?
Yes. So we can write x03 square plus y03 square is going to be a3 plus d3 square, right? Now I can say a3 plus d3 is the square root of x03 square y03 square. And then d3 is y03 square minus a3. All right, I found this little guy. Now I have to find theta 1. So I'm trying to find linear relationships that are either a function of the xy z of end effector or the element of this robot, like link values or something, right? So that just makes your life easier. How do we find theta 1? What's the relationship for theta 1 that depends on those things I just said? Let's see. No. Who's my next victim? Connor is my always victim. You gotta do. You can ask for help. Alex? That's not a very reliable thing. So look at theta 1. You know the length in front of it, right? And then you know the adjustment one too. Go back a few years ago to trade. Can you find? I'll tell you the sine, cosine, and then. Okay. You know, easy it is if you have a reliable friend. Alex? All right. Obviously, I'm joking. They are solving a lot harder problems. Usually, the simple problems are the one that doesn't come to our mind. Because can it be just simple? Like, yes, it could be tangent of theta 1 is y3 over x03. This gives you theta 1 is tangent inverse of y03 x03. That's our third. Right? Now we have equation for all of those. Basically, we found expressions, right? So I'm gonna bring them all here and I'm gonna give you something to do with them. Copy, paste. All right, now, if we had A1, A2, and A3, for any given point, you should be able to find theta 1, D1, well, D2, D3, and theta 1, right? So example is here for A1, 1 meter, A2, 1 meter, A3, 0.3 meter, find joint variables. Joint values, I can say now, because it's going to be numerical values. Joint values to reach 0.513 meter. So this is the end effector. So you want your end effector to reach to this position, right? What are your theta 1, D2, and D3? What is D3? I found D2 because this was easy. Mary, did you find D3? No? Yes. 0.818 meter. How about theta 1? Let's see. Victor? You haven't gotten there, have you? Haven't done, okay, haven't done the calculation. Okay, so yeah, so 1 over 0.5 is 2, right? So tangent inverse of 2 is, well, you will use your calculator, for example. So. I'm not gonna be like, no. All right, degree. So what does it mean? So this problem would be, here's your robot. For a cylindrical robot, if the end effector has to reach to 0.513 meter, that's the coordinate, what are the joint variables? So these joint variables translate into what? The rotation is your DC motor or servo motor rotating 63.43. However you want to send the command. Your prismatic joints are probably your linear actuators, right? You have to actuate and go linearly 0.8 in one direction and the other one has to go 1. And this will send the system to that position, right? Make sense? Now, if you want to make sure that your solution is correct, these are the values that if you use them for forward kinematic, you will find out the position of your end effector will end up here. So the inverse kinematic is basically the inverse of forward kinematic, and hence the name inverse kinematic. Cool. Everything makes sense? Hopefully. So this is your class participation, but go to Carmen. I have given you the end effector coordinate for where you have to reach. And you will have A1, A2, A3, and 4. But before that, you have to find out the expression. Find the expression, plug the values, find the end, submit everything. All right, that's your 5 plus 3. I will solve part of this for you, but I will let you work on it for about 10 minutes first. And I'm gonna close Zoom. No, I'm gonna keep Zoom open. Just gonna pause. Hmm. What does So I just, so I draw x0, y0 plane and x0, z0 plane, but I didn't show the drawing variables. I want you to do it. And I also didn't show like x to y to but you should have something like this when you reduce. This is, if you make a mistake here, then the rest of them will be wrong. You're done. Second video. Another plane to it. I'm going to- this- I don't know. I cannot- yeah, this one. Don't think it is. But I wanted to show you what I included it. Because you say yes, but imagine, so it's not on Monday, you have to do it on all. This, you have to submit all of them for the. You have to put, if you go to Carmen, you see I have given you values for all of that. So make sure that you check Carmen to get the numbers, because I need the solution to matter. If you have four. Submit whatever you have by four, right? This is again class participation, making sure that you understood what's going on. And you have like as far as you can get. Yes. So this is the first, right? So this is this or minus this. And then once you're done, you can actually mentally visualize the part. Huh? Did you find a mistake?
Yeah.
Okay. So your default will be whatever you choose. You have to have the word that you use. Something will be more difficult because you have the Yeah, like if, like for the prismatic, obviously it has to be positive. If it's someone who's negative, what does it mean? You know, crack into the- That's only one of the error. Oh, yeah, we can.
Yeah, we should get the video. I'm worried that I'm going to like with we didn't air checking.
I'm gonna close this because